In this lesson, we'll cover both the product and quotient rules. To start with the product rule, it says that if you take the derivative of a product of two functions, it will equal the first times the derivative of the second plus the second times the derivative of the first. So when encountering a product, you can't just take the derivative of both to get your answer. You leave one alone, multiply by the derivative of the other, and then you switch it. Leave the second alone and multiply by the derivative of the first. Let's try that in example 1, where I want to take the derivative of x squared times e to the x. So here we have two functions. The first function is x squared, and the second function is e to the x. According to this rule, the derivative is, we'll leave the first alone, so that's x squared, and we'll multiply by the derivative of the second. Now the derivative of e to the x is just e to the x, so that is the derivative. Now we add on the second, which we leave alone, which is e to the x, and we multiply this by the derivative of the first, which is 2x. And here it is. The derivative of this product is this function here. It was the first times the derivative of the second plus the second times the derivative of the first. Now you can simplify these, and I think I'll do that in this example. I see common to both terms is an x and an e to the x. So you can factor out x and e to the x. And what is left over is x plus 2. The important part of this lesson is simply to take the derivative. And simplifying isn't extremely necessary for understanding how these rules work. However, in future lessons, it'll be nice to simplify the derivative in case you'd like to figure out, let's say, where this thing is equal to 0. When it's factored like this, you can look and say, oh, well, this whole thing is 0 if x is 0, e to the x is never 0, and x plus 2 is 0 if x is equal to negative 2. But I'll leave it at that for this question. So in example 2, we will continue applying the product rule. Here I have a function h of y, and I'd like to find its derivative. So here we have a first function and a second function. So if our goal is to find the derivative of this function y, it's the first times the derivative of the second, which is 2y, plus the second times the derivative of the first, which is also 2y. Now we can simplify this a little bit. H prime of y is equal to, if I multiply in the 2y, we get 2y cubed plus 2y. And if I do the same thing over here, distribute in the 2y, we get another 2y cubed, but this time a minus 2y. And we have like terms. 2y cubed and 2y cubed is 4y cubed, and this cancels with this to give us our final simplified answer of h prime of y is equal to 4y cubed. There is a second way to solve this problem, and for all these questions, there might be multiple methods that you can use. Before actually taking the derivative, because there's a plus and a minus, and these two factors are pretty similar, this multiplies pretty easily. You get y squared times y squared, which is, this function is also y to the fourth, and your middle terms are a negative y squared and a positive y squared, and they cancel. I'm not even going to write them. But 1 and negative 1 multiply to minus 1. If you take the derivative from here, you get, well, you don't even have to use the product rule. You can bring the 4 down front, copying down the y, subtract 1 from the exponent. The derivative of 1 is 0, and you also get 4y cubed. So sometimes if you can quickly multiply and take the derivative, this might be the way to go. But this method worked too, and we actually did get the same answer. Now, in part B, here it's kind of similar where, well, there's this plus minus thing going on, but these terms aren't identical. There's an x here and there isn't one here. For this reason, I'm not going to multiply this out. Instead, I'm going to call this the first, and I'll call this thing the second, and go directly to the product rule. The derivative of this thing is the first times the derivative of the second, which is 5 minus e to the x, plus the second, and then multiply that by the derivative of the first, which is e to the x. You can multiply this out and you can multiply this out and combine like terms, but I'll actually stop here for this question just because we did take the derivative. The other rule in this lesson is the quotient rule, and that's when you don't have a product but you have a fraction or a ratio of two functions. I'll start by stating the rule. The rule is you take the denominator, so you don't take its derivative, but you multiply that by the derivative of the numerator. You then subtract and you reverse the situation. You say, well, I'll leave the numerator f alone and multiply that by the derivative of the denominator. So it kind of resembles the product rule. There are a couple of differences. There's a minus instead of a plus. And because there's a minus here, it's important that you start with this term. You can't simply just interchange these two. It'll always be the bottom times the derivative of the top first, and then minus the top times the derivative of the bottom. And the other big difference is once you get that expression, you take the whole thing and you divide it by the denominator squared. It is customary to typically not square out the denominator, but leave it to the power of 2. And we'll actually see that in a couple of examples. Like this one here. I want to take the derivative of the function f of x, which is definitely a fraction. It's a ratio of two functions, so I'll use the quotient rule. F prime of x is equal to, well, I take the bottom, which is x minus 3, and I multiply that by the derivative of the top, which is 1. I subtract off the top times the derivative of the bottom, which is 1. And I take this whole thing, and no more derivatives, but I divide it by x minus 3 squared. I think this will simplify pretty well. Here I can call this whole thing x minus 3, and I don't really need to write this 1, but I'll distribute this negative into the parentheses. So f prime of x is really equal to x minus 3 minus x minus 1. Again, that came from, there's really a negative 1 here that's being multiplied into the parentheses, and this is divided by x minus 3 squared. And let's see, next we could, in the numerator, we have x and minus x. Those cancel, and minus 3 minus 1 is minus 4. Completely simplified, this is the derivative of f. So here in part B, I have a function capital F of x, and it's a fraction, so I'm going to use the quotient rule to find its derivative. F prime of x is equal to, okay, so I start with the bottom. That's 5x cubed minus 2x squared plus 1, and I multiply that by the derivative of the top. The top is 1. Actually, the derivative is 0. That's 0 times this whole thing, which will eventually become 0. I subtract off the top, and I multiply that by the derivative of the bottom, which is 15x squared minus 4x. And this is all divided by the denominator, 5x cubed minus 2x squared plus 1, and that whole thing squared. I am not going to square this out. I'm going to leave it to the power of 2. Typically with the quotient rule, nothing will be gained by squaring this in terms of trying to simplify the answer, so I'm just going to leave it alone. But in the numerator, like I said, this whole thing is 0, and I have this negative 1 that's going to be multiplied into the parentheses, so this gets multiplied in, and my answer is f prime of x is equal to negative 15x squared plus 4x, all divided by, and then we have 5x cubed minus 2x squared plus 1, all squared. You could factor an x out from the numerator, but I think this is pretty good, so I'm going to leave the answer just like this. So in example 4, again, just a little more practice with using the quotient rule. You can try it first if you'd like. Let's see. If I want to find f prime of t, I have to use the quotient rule because it's a fraction. That's the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the denominator, the bottom, squared. And I think it'll be worth simplifying the numerator, but But again, I'm not going to square this out. I don't think it's going to benefit us in any way. So I will multiply in this 8, and I'll multiply in this negative 8t, and we'll see what we get. F prime of t is, we have 8t squared plus 8t minus 8, and then we have minus 16t squared minus 8t, all divided by t squared plus t minus 1 squared. Are there any like terms in the numerator? Okay, we have an 8t and a negative 8t, so those will cancel. This will remain, and here we have an 8t squared minus 16t squared. It'll leave us with, in this case, a negative 8t squared minus 8 all over t squared plus t minus 1. And I do see that in the numerator, you could factor out a negative 8. So, I mean, maybe we could write it like that. Factor out the negative 8. We're left with t squared plus 1, which cannot be factored. And then we also have t squared plus t minus 1 all squared. I think either of these answers is fine. And that is it. So in this one, here f of x is x to the 6 times e to the x, all divided by x to the 6 plus e to the x. Again, you can try this one first if you would like. Okay, so using the quotient rule, it's the denominator, the bottom, times the derivative of the top. Okay, in the numerator, we actually have x to the 6th and also e to the x. That's a product. And we have to take the derivative of the numerator. So here I actually have to use the product rule within the quotient rule. The product rule says it's the first times the derivative of the second plus the second times the derivative of the first. And I'll subtract the numerator, which is x to the 6 times e to the x, times the derivative of the bottom, which is 6x to the 5th plus e to the x. So kind of a mess. And this whole thing is divided by x to the 6th plus e to the x, all squared. And I'm not going to square this out. I'm going to leave this alone. But in the numerator, I think I am going to distribute and try to collect some like terms here if possible. Well, I think I'll start by multiplying in this x to the 6th and then this e to the x. And maybe I'll note up at the top, if you have e to the x, and that gets multiplied to an e to the x, that will give you e to the, well, x plus x, because you add the exponents if your bases are the same. And that simply is e to the 2x. So I'll use that when I start multiplying this stuff together. So to simplify this thing, okay, that's x to the 6th times this thing. An x to the 6th and an x to the 6th is x to the 12th. So that's x to the 12th e to the x. I'll then take this and multiply it here. That will be, and I see I made a mistake. I don't know why I put a 4 here. That should really be a 5. So I'm going to go ahead and just change that. Whoops. With that fixed, this times this is 6x to the 11th and an e to the x. I'll now multiply in e to the x, which when multiplied here will give me this e to the 2x. And the same thing will happen when it gets multiplied here. So first I get x to the 6th e to the 2x. And then here I get 6x to the 5th e to the 2x. And lastly, I can now distribute this into these parentheses. We'll get that's going to be negative 6 x to the 11th e to the x. And then also a negative x to the 6th e to the 2x. All divided by x to the 6th plus e to the x squared. Any stuff cancel? Hope so. here we go. This is the opposite of that, so those will cancel. Oh, we have this, which will cancel with this. And the only thing left over is this term and this term, which have common factors. So let's see what that is. F prime of x is, so that's x to the 12th e to the x plus 6x to the 5th e to the 2x all over x to the 6th plus e to the x squared. Okay, if you want to try to factor out common terms from these two parts, these two factors, you can take out an x to the 5th and a single e to the x from both of those, because this thing is really the same as this. I'll try writing it factored. This is f prime of x is equal to, so we're taking out an x to the 5th and an e to the x, and what is left over is x to the 7th, and then also 6e to the x. And this thing here is the final answer. In example 5, we're told that f of x is equal to e to the x times g of x. And g of x is some function that we don't have a formula for. However, we're told that we can assume g of 0 is 3, and its derivative at 0, g prime of 0, is 5. Can we use that information to find f prime of 0? Step 1 is, if you want to find f prime of 0, you have to find f prime of x. So I'll start there. So what is f prime of x? Well, we have a product of two functions, e to the x and g of x. And the product rule says it's the first times the derivative of the second. And the best we can do is just write that as g prime of x. We then add on the second and take the derivative of the first, which is e to the x. With this formula, if we're looking to find f prime of 0, we can plug 0 into our equation. And if we know what each part of this is equal to, we'll have our answer. F prime of 0 is equal to, well, e to the 0 is 1, and g prime of 0, according to this up here, is 5. I then add on g of 0, which we're told is 3, and this again is equal to 1. So what is f prime of 0? It's 5 plus 3, and that is equal to 8. Example 6 is kind of similar to example 5, but instead of having a product, we're going to deal with a quotient. All of this symbol here means we're going to take the derivative of h of x divided by x. Now this line with this x equals 2 at the bottom means after you take the derivative, you want to put 2 in place of all of the x's into your formula. So here we don't actually have a formula for h of x, but we're told h of 2 is 5, and h prime of 2, the derivative of h at 2, is -9. That should be enough information to figure out what this is equal to. And just like last time, step 1 is going to simply be, can we just take the derivative of this? And if we get a formula for it, can we put 2 in place of all the x's and simplify it? The quotient rule says the derivative of this is the bottom times the derivative of the top minus the top times the derivative of the bottom, and the derivative of x is 1. And this is all divided by x squared. Not a whole lot to simplify, but I'll just rewrite it one more time here. This is x times h prime of x. Really, you can just put minus h of x and divide this by x squared. Now, to figure out what this is equal to evaluated at 2 means put a 2 in place of all of these x's and simplify it. That is, d dx of h of x over x evaluated at 2 is 2 times h prime of 2 minus h of 2 all over 2 squared. That should just reduce to a number. Let's see, that's 2 times The derivative at 2, we're told is -9, so I'll put -9 here. I'll subtract off h of 2, which we're told is 5, and we're dividing this by 2 squared, which is 4. Okay, so that's -18 minus 5, and -18 minus 5 more is -23, and 23/4 is an exact answer, and that is what this derivative is evaluated at 2. I'd like to conclude this lesson by demonstrating why the product rule is true. So this is a proof. That is, if we assume both f and g are differentiable, that just means you can take the derivative at some number a, then this is a true statement, where if you take the derivative of this function, which is a product, and put a in place of all the x's, you'll have the first times the derivative of the second plus the second times the derivative of the first, all evaluated at this number a. Within this proof, we're going to use the fact that if f is differentiable at a, then it's also continuous. For both of these functions, f and g, since we're assuming it is differentiable, they're both continuous at this number as well. So how does this proof work? When we say we're taking the derivative of a product of two functions, and we don't know that the product rule is true, what do? Well, we have to use this. The limit, as h goes to 0 of, this entire function evaluated at an x plus h. And what's that? That's f of wherever I see an x, I'll just put an x plus h. And we subtract off the function itself, which is f of x and g of x. We should be able to take this limit definition and break it apart so we end up with something that looks like this. I'm going to do a trick. Within the numerator of this, I'm going to add in what is essentially 0. If you were to add 0 into the numerator of this fraction, well, it doesn't change the value of the fraction. Kind of like multiplying by 1 would not change the fraction either. But the way I'm going to write 0 is going to look a little odd. This is the limit as h goes to 0 of. So we have this f of x plus h, and we have this g of x plus h. I'm now going to subtract, and I'm going to do a kind of combination of this term and this term. I'm going to subtract f of x plus h times g of x. But at the same time, I'm going to add it back in. And then I'll copy down this minus f of x, g of x. Now, this is definitely equal to 0. So we added 0 into the numerator. So this fraction should be equivalent to this one. Why does this help us? If you look at these first two terms, there's now a common factor of f of x plus h, which means you can factor it out. If you group these two terms together, there's this common factor of g of x, which you can factor out as well. And that's my next step. I'm going to say, well, this is the limit as h goes to 0 of. I'll factor out the f of x plus h. And what's left over? G of x plus h minus g of x. And at the same time, in the second two terms, I'll factor out the g of x. And what's left over is f of x plus h minus f of x. Now, this whole thing is divided by h. That means I can actually split this up into two fractions and then just say, okay, well, it's this whole thing divided by h and this whole thing divided by h. This line and this line are equivalent to each other because we have a common denominator. You could add these back into a single fraction where h was the only thing in the denominator. And furthermore, just to kind of make this look a little bit nicer, I'm going to just consider it like this. This is f of x plus h times this part. And over here, again, I could put this in its own fraction and just divide the h into here. So just so it looks a little neater, I'm going to erase this and put it like this. And we're saying we're taking the limit of this whole thing. That's f of x plus h times this fraction plus g of x times this fraction. This thing is starting to kind of look like the product rule. It's one function f times this thing. But as h goes to 0, this is g of x plus h minus g of x all over h. That's the derivative of g. So I'll just make note here. If you look at just this thing, as h goes to 0, this thing will start to become the derivative of g. Likewise, over here, as h goes to 0, this thing is the definition of the derivative of f. So as h goes to 0, this gets closer and closer to the derivative of g. Likewise, this gets closer to the derivative of f. Nothing happens to this because there's no h in it. And over here, as h goes to 0, this should approach f of just x. And that's our final step. That's our conclusion. We can say, well, this is equal to f of, I'll put x plus 0 times the limit as h goes to 0 of g of x plus h minus g of x all over h plus g of x times the limit as h goes to 0 of f of x plus h minus f of x all over h. Essentially, distributing the limit to these two pieces. And as this goes to 0, I get this. I put the limit in front of this whole thing, and now this is the derivative of g. Nothing happened to this function, and if I take the limit of this, it's equal to this. This part is f of x times g prime of x plus g of x times f prime of x. To make it look like this rule here, if you evaluate this thing at a, you're just putting an a in place of these terms, and essentially this concludes the proof. One last thought is, why do we need to know that f is continuous? And that's from this step here to this step here. Here, we were taking the limit as h goes to 0 of f of x plus h. And I said this is equal to f of x plus 0, which is f of x. Why is this true? This is true by continuity. This limit exists, and it's equal to the function at x. So let me just make that a little bit neater. That's equal to f of x. So this is true by continuity. And since f is differentiable, it's also continuous, which is why we can take this limit and simply call it f of x.